bonjour, good morning. Thank you for having me. I'm Jonathan Hurst. I'm Chief Robot Officer at Agility Robotics. This is our machine, Digit, humanoid robot. And I'm going to talk today a little bit about how we go from the ambition of having humanoid robots that are part of everyday human life, multi-purpose, useful in many, many places, but how we start with that, how we have real-world impact right up front on our path towards this big dream. I think that this is the best crowd to really agree with me and not argue too much that embodied AI is the future of labor. We're going to have machines that can physically do most of the things that people can do, and then many, many more things beyond that, and that's going to fundamentally change how we do labor. Now today, it starts in things like logistics and warehousing and some simple, more focused tasks, but over time, it's going to gradually broaden towards more manipulation tasks, better and better dexterity, and other things to get out into more and more broad markets. And there's two big main ways in which I believe that embodied AI broadly, but also humanoids, are going to impact our economy. Number one is basic capacity. Just the limit that many of these industries have on the services that they can provide to customers because there are not enough people to do the jobs and do the roles. Especially with demographics changing and especially with population shifting, this is a really important one. But also basic capability. You can ask the question, how many blacksmiths does it take to build a laptop? And of course, blacksmiths can't build laptops. You have to ladder up the technology to get to the point of creating something like that. And embodied AI is going to do that. Now that's the hardest to predict. It's hardest to know what we are going to be building in the future that these embodied AIs allow us to build, but I do believe that this is going to be a major important factor in our economy. So the big question is really important to ask, and it's important for anybody building humanoids to ask this, is why a humanoid? And is it even the right way to do it, or should it be something else? And I would say we are building human-centric robots because we want to operate in human environments. And this is really a new era of robotics. Robots in the past have really you've had to design the environment around the robots. Industrial robot arms, you design the process. Even AMRs, autonomous mobile robots, you have to have an environment and a space that's really suited for the robots. But having human-centric robots is what allows them to be much, much more general purpose, more multi-purpose, because so many workflows have been designed around us. We've designed the workflows around us. So having a robot that can just walk in and do that workflow is very, very useful. Now, we have also found at Agility, as we've really looked into this, that it is useful to have kind of a rough form factor like a person. You want two arms to pick up big things. You need to be balancing in order to be able to lift big things up high and do it in narrow spaces like hallways and go through doorways. To do that, you have to be balancing. You have to be dynamically stable. And a pair of legs is the best way to be dynamically stable. Legs can be more stable than any other solution that we've seen or that we know about in order to be balancing. So upright torso, balancing, bipedal 2 legs, and bimanual 2 arms. And then, because this is human-centric, having a face, having something to be able to interact with people. But that's kind of where I think some of the similarities may end. And a big question is on hands. We see so many 5-fingered hands, for example, but why are we building 5-fingered hands? I don't believe anybody knows the answer to that. Dexterity is one of the grand challenges in robotics. We don't do it well in robotics right now, certainly nowhere near human dexterity. And I think when you copy it, it's kind of like the Disney Hall of Presidents. It's an animatronic. It maybe looks on the outside a bit like a person, but it's missing all of the most important things like force control and compliance, and of course the intelligence in order to create that dexterous behavior, even if the hardware is physically capable. We found with Digit, for example, there was no 5-fingered hand on the market that could do what it does. It's lifting 25-kilogram bins. That's very difficult, actually, to grasp it like that. And so we did build very powerful, strong manipulators. But we have generality, because now you can swap manipulators out. A humanoid robot has the ability to use different tools for its task. Now, I think down the road, we may be going by 2 or 3 fingers to start with. We see in like the Cybathlon, which is a competition in Europe where disabled people can augment themselves technologically by adding whatever they want. And so amputees can have manipulators, and then they do a manipulation challenge, which is just measuring pragmatically what can they do. And the winner the last 2 years has been a parallel jaw gripper, a very simple parallel jaw gripper with a 1 or 2 degree of freedom wrist. So that tells us something about if we really want to achieve dexterity, we've got to think about this from the first principles approach and not just copy the way that people look. Now, the intelligence is a huge part also of how you need to solve this grand challenge of manipulation and whole body control and locomotion, all of these things. And I think it's very important to point out that there is no single silver bullet. There is no black box of AI. There is a big tent of computational tools that are all very valuable in creating the behaviors that we want. And different tools are useful in different locations. So I already talked about the hardware. It really has to be special. You have to get the physics right of the mechanical system. It has to be back drivable, have good force control, be able to have good compliant interaction with the world to make it even possible for any software, no matter what it is, in order to locomote and manipulate things in the world. At the high level, at the very top of this stack, we see large language models and vision language models and things like that that could be trained off of the entire internet. And that helps with context and solves perception and so many things. But it cannot control an individual robot. It cannot control the torques to all of the individual motors at every instant in time, given the particular sensor inputs, because there is no source of data that provides examples or correct examples of that. That has to be discovered. So there's 2 ways to do that. One is you teach the robot via teleoperation or animation or motion capture or other examples. And we see that for teaching the robot sort of complex skills. How do you grasp things? A learning from demonstration. But then robots have to practice. Robots have to use reinforcement learning and simulation in real life on physical robots in order to refine that, in order to actually get the high performance that that robot is going to be able to achieve, beyond what a person controlling a robot would be able to do. So all of these things, there's a lot here. So the question is, how do we get to this? If we solve these grand challenges in robotics, we can have these machines working with us and helping us in our homes. I certainly hope to have this by the time within my lifetime. But today we can start with picking up bins, picking up totes, doing things in warehouses and logistics, doing useful work that customers are willing to pay for right now that provides a return on investment and lets us learn all of the very hard things about deploying robots. There's a lot about information security, about all the metrics of uptime and servicing these robots, and safety is the big one I'll talk about. So we have deployed Digit doing work like this is in a GXO warehouse. You can see that Digit is picking up bins off of the autonomous mobile robot and putting it on a conveyor belt. This is something we've been doing for almost 2 years now. And this is a commercial deployment. Here it is at Amazon, stacking totes. You can see it's a different workflow, but very similar in many ways. So we're kind of scoping a multi-purpose task within a range of scope and can gradually build that scope over time. Here it is at Scheffler, loading dirty, oily parts into a washing machine. So these are fairly heavy. These bins are sometimes damaged. They're always a little bit different. They're always a little bit different weight. There's shifting weight inside of it. And Digit's just doing this basic workflow. So what's the real blocker? Yes, we've deployed, and we've been deployed for a couple of years, but really it's safety. I'll go back a couple and see there's a work cell around this robot. There's a physical barrier that is separating this machine from any people that would be nearby. This is the only way that we can operate within the existing regulatory environment that we know of. Any dynamically stable, any balancing machine is going to need to be behind a physical barrier like this, which really limits its utility. A robot that has to be in a cage is not very multi-purpose. It's not utilizing the benefit that a humanoid robot can actually utilize. Being human-centric requires being safe. It requires being able to go out into unmodified human environments. And safety is the blocker right now because these robots can do the physical work. So step one, well, I'll start with this. You know the robots will fall. That's unavoidable. That has to be acceptable. It has to be okay if the robot can't land on somebody's foot and cause even a basic injury like that. Basic pinch point kinds of things, right? But beyond the basic pinch points and hot surfaces and the robot falling, judgment errors when a robot is making intelligent decisions in an environment, like you don't want it to pour hot coffee in your lap or start the dryer when there's a kid hiding in there because they're playing hide and seek, or any number of things like that that we haven't begun to envision, the world hasn't begun to envision yet, but will be necessary before we can deploy these in homes and environments like that. And there's a lot of rules about, even social rules, but also basic safety rules. A robot has to make intelligent choices about whether it touches you on the shoulder or the eyeball, and which one is okay. And it has to do that not just 90% of the time, but in sort of a statistically, true 99 point, some number of nines%, validated by third parties, such that insurance companies can understand the risk that they're undertaking. It is a huge, very, very high bar to get there. And they cannot do this now. So step one is operate inside of the safety cage. But a whole bunch of other things like a control pendant, safety-rated power electronics, safety-rated data bus, so that when you hit the e-stop, you have a well-known and well-understood behavior that, again, a third party has validated. It's not just you stating that this should work. It's somebody else who's gone through this design with a fine-tooth comb, and it's a lot of certification. Step two, and this is what Agility is releasing later this year with our Digit V5 robot, is a machine that can detect people around it and change its behavior as people approach. So the robot can slow down, it can stop what it's doing, set its load down on the ground, and even get down on the ground and sit down and turn power off before a person can touch the robot. This allows a robot to get outside of a safety cage, outside of a work cell, and still operate in human environments, in human spaces, near and among humans. Now that's a necessary step in order to get to step three, which is where we'd really like to go, is robots being able to make those intelligent decisions about what they can touch and how they can touch them. And we believe that this is going to follow a similar path to what we've seen from autonomous vehicles. Now in autonomous vehicles, we had safety drivers and collected millions of hours of data and start to be able to predict what a pedestrian or a bicyclist will do and be able to react appropriately to that in a way that actually allows these robots to be autonomous. Now, of course, with a humanoid, the complexity is vastly greater than cars on the road. Cars have 2 degrees of freedom. They can go faster and slower, and they can steer right and left. Humanoids, of course, have so many more degrees of freedom. And roads are far more structured than homes and workplaces and social rules and human environments. And we cannot have safety drivers on a robot. There's no real way to have a robot be safe and also productive if you have a person controlling it the whole time. So that's why I say step 2 is important, because now we can have a fleet of thousands and thousands of robots deployed, doing useful work, collecting data, while we build the safety setup for the intelligent decision-making of a robot, and build the statistical case that shows reliably that these robots do what we expect them to do and make the intelligent choices. That's how we get to robots that operate safely among us and in human environments, and even get to the point where you can hand them something and physically interact with a humanoid robot, which is not possible today. So we want to start with what robots can do right now, and that's logistics and warehousing and that kind of semi-structured industrial work that's still too unstructured for automation to serve right now. People are still doing this task, but Digit can walk in and start doing this job and be a source of automation without installing additional infrastructure. And then we continue to build out the use cases in terms of each picking and dexterous manipulation and safety, and get into broader and broader markets and start to cover more and more of kind of the general labor and doing physical work in the world. This is the path. In order to get to broad, in order to achieve this general purpose dream, we need to start with focus. We need to start, if you're going to do 100 use cases, you start with 1 use case, and then 2, and then 3, and you work your way up. And what's really exciting about humanoids that is not the case with autonomous vehicles, an autonomous car has to be fully safe and fully autonomous and above a certain bar before it's useful. A humanoid robot can be in more semi-structured environments today and step out of the work cell today and be useful and get to the scale of hundreds of thousands of robots and be a huge market, even very early here, in doing logistics and warehousing and manufacturing and that sort of thing. But then, building on all of that, you start to expand out into retail markets, and you imagine a robot working in a grocery store, palletizing, depalletizing in the back, but then also unpacking boxes and coming out and being able to stock shelves and being able to start to operate close to people, and then through that path, eventually getting to the point of hospitals and construction sites and home and everything else. And that's where I'd like to stop. Thank you for attention. We're very excited about humanoids getting out into the world. Thank you.